Our planet, the stars, the distant galaxies, and even the universe itself were formed after a loud explosion called the Big Bang that happened several billions of years ago. And since then, our solar system has continued to expand and evolve tremendously. But what exactly happened at the very beginning? And what does the future hold for our solar system? Let's find out. The Big Bang is a loud explosion that produced a large concentration of interstellar dust and hydrogen gas into the atmosphere. While this was going on, a large small ball that scientists describe as the universe was getting heated at a remarkable pace and slowly expanding into what we've come to know as the universe today. Critically, the universe and the solar system are two different things. The universe is a large expanse of free space that contains several celestial elements and planetary systems, including our solar system. One of the biggest differences between them is their age. While the universe was formed about 13.8 billion years ago, our solar system is said to be about 4.6 billion years old. Following this process, most stars forming in our galaxy included those of the Orion Nebula that were surrounded by disks of dust and hydrogen gas, popularly called circumstellar disks. In addition, other dust and ice debris occasionally collided and merged to form larger bodies that eventually became planetesimals. This process most likely happened approximately 4.6 billion years ago. The planetesimals that formed were quite small, measuring a few kilometres across at most. According to the best available data, the planetesimals located in the inner and hotter part of the nebula were largely composed of silicates and metals. Meanwhile, those in the outer and cooler regions of the inner planets were predominantly made of water ice. At the same time, a group of protostars, possibly including the Sun and the Moon, began to form from the cloud of debris left by intense star explosions in the Milky Way galaxy. After the formation of the planets, the terrestrial planets that make up the inner solar system began to take shape. At the time, the planetesimals were big enough, so big that their gravitational pull was strong enough to influence other planetesimals. This process increased the frequency of collisions, causing the largest celestial bodies to grow very quickly and eventually become planetary embryos. Consequently, the accrete continued until only 4 large bodies were left standing. These large bodies are what we know today as Mercury, Venus, Earth, and Mars. At the same time, a Mars-sized planet rammed into Earth, causing a violent collision that led to the formation of the Moon. Around 4.59 billion years ago, the gas giant planets like Jupiter, Saturn, Uranus and Neptune were all formed. All of these monster-sized planets constitute the outer solar system today, except that Uranus and Neptune were thought to have formed closer to the Sun than where they're currently situated. According to historic observation, one or more amigos may have been formed as well, but they were most likely ejected from the solar system during the countless evolution phases that had occurred in the past. But most likely, they must have been extinct before 4.55 billion years ago, when the Sun began fusing hydrogen into helium. During this process, the solar nebula witnessed several solar storm ejections. The evolving proto-sun accumulated some of the nebula's material even before some of the planets in the outer solar system were formed. Consequently, a small portion of the proto-sun was absorbed by the planets. However, the remainder was swept away when nuclear reactions were triggered in the core of our Sun. These reactions triggered a strong solar wind which expelled the Sun's outer layers even far beyond our solar system. Nowadays, a much weaker solar wind continues to flow across the outer solar system. Between 4.5 and 4.1 billion years ago, the Sun gravitationally separated from its protostar siblings. Then came the era of the formation of asteroids and comets. Both elements are basically rocky remnants from our early solar system, except that asteroids are rocky in nature, while comets are made of ice and dust, as well as other materials left behind during the formation of the original nebula. Interestingly, both asteroids and comets travel through the solar system, but they have distinctive features that allow scientists to identify and differentiate them. For instance, comets occasionally perform close flybys around the Sun to heat up and release a long tail of dust and gas. Between 4.1 and 3.8 billion years ago, the orbits of giant planets shifted, causing small worlds throughout our solar system to scatter. Quite a few of them bombarded the inner planets and most likely were responsible for the formation of water and organic materials on Earth. However, a large concentration of these planetesimals were holed up in a small region beyond Neptune, popularly known as the Kuiper Belt. Pluto, our former neighbour that was reclassified as a dwarf planet a couple of years ago, is one of the biggest celestial objects in the Kuiper Belt. About 4 to 3 billion years ago, small world bombardment triggered widespread volcanism on the inner planets. Eventually, these planets became heated and their interiors are melted and reorganised into layers of different densities. According to reports, the melting is caused by a number of processes, including the heat emanating from impact striking and accepting the sinking of heavy materials to the centre and the decay of radioactive elements. These adjustments and reorganisations gave the rocky planets dense, metal-rich inner cores, less dense mantles, and outer crusts formed from the highest materials. About 3.8 to 3.5 billion years ago, life forms began to take shape on Earth. At the same time, abundant water ice and oceans were said to have been formed in the northern lowlands of Mars. As the Martian world cooled, the water was then collected as ice beneath the surface and in the polar ice caps. However, scientists estimate that both the water bodies and the atmosphere on Mars were lost around 3 billion years ago. Some 2.5 billion years ago, photosynthetic organisms began to evolve on Earth. These organisms are responsible for pumping oxygen into our atmosphere and creating the blend of helpful gases we breathe today. Fast forward to 1 billion years ago, when the volcanism on the Moon stopped. About 100 million years ago, an asteroid impact on the Moon caused the Tycho crater. At the same time, Mother Nature was beautifying Saturn with its glowing rings. More recently, about 66 million years in the past, a giant asteroid struck our planet. This caused a devastating change to all of the normal life processes, including severe climate change and the extinction of dinosaurs, along with 1/3 of all the species of life on Earth at the time. Nowadays, aside from the occasional asteroid attack, our solar system is much more stable. But what does the future hold? Well, the predictions vary depending on which astronomer and data you consult. But according to scientists, our Sun running out of fuel is one event that is bound to happen. The estimated time for this occurrence is believed to be between 5 and 6 billion years from now. During this period, all of the Sun's hydrogen elements would have been converted to helium, which would in turn fuse together to form carbon. This reaction is expected to happen at much higher pressures and temperatures than hydrogen fusion, meaning that more energy will be released. This extra energy produced in the core will spread across the outer layers of the Sun far beyond its current position. As they travel to the outermost layers of the Sun's atmosphere, the temperature drops from 5,700 degrees Kelvin to around 4,000 or 3,500 degrees Kelvin. At this point, the Sun will swell up and become cooler and redder, much like a red giant. The expectation is that the radius of the Sun will expand rapidly during this phase of evolution. Consequently, its outer layers will most likely engulf the surrounding planets, including Mercury, Venus, and quite possibly even Earth. Ironically, even if our Earth manages to escape direct contact with the solar atmosphere, everything within it would be doomed anyway, because the solar luminosity will rise by several thousand as it becomes a red giant. The process would heat the Earth to a temperature of about 2,000 Kelvin and cause catastrophes all across the solar system. But thankfully, the red giant phase of the Sun isn't something that will last forever. About 1 billion years from now, all of the helium in the Sun's core would have been depleted, and it wouldn't have enough mass to drive pressures and temperatures high enough to fuse carbon into heavier elements. With no energy source at its centre, the Sun's luminosity will be reduced remarkably. Eventually, the Sun will transcend from being a red giant to a white dwarf. At first, the white dwarf version of the Sun will be very hot, about 40,000 Kelvin or thereabouts. But eventually, it will become cool after several billion years, and its light will become so dim that the Earth's surface will become extremely frosty, more than 100 degrees below zero.